Welcome our guest, Dr. Martin Fischer from DLR. Martin is the group leader for human-centered simulation at DLR. And at set level, he's the leader for simulation use case 2 that we just learned about. And there, especially for the tool development coordination, DLR research implementation. Martin is an expert for simulation, human-computer interaction, and I found a paper that he published in 2020 where Martin asked the question, isn't a driver in the loop study just a serious version of a video game? And I'm very excited to hear some thoughts about that, if that influenced your search at the set level project. Martin, welcome.
Okay, thank you, Laura, for the kind introduction. The topic of today is indeed quite different to the question you just raised. So after listening to the first session, I think you got a really good overview about the set level project. And now we will start to dive a little bit deeper into certain topics. And so I will start with that by looking a little bit more detailed on the topic of simulation architecture. And besides the architecture, we will come along some aspects of some procedural issues, and it will be again, I have to say, because you heard it quite a lot and will. Furthermore, standards will be as well play a role in my presentation. First of all, the motivation. Why did we, from the beginning of the project, discussed simulation architecture, and where comes our motivation from to spend time on that? So first of all, we wanted to achieve a flexible and modular architecture based on common simulation standards. And here are a few reasons why we think that this is really worthwhile spending the time. A good architecture enables flexibility of simulation setups. You have a lot of different simulation tools and setups, depending very much on the simulation task you want to solve. So flexibility enables you to be faster in your simulation development. You always want to have a tight consistency and connection between your test case and the simulation you carry out. Furthermore, you want to reuse elements of the simulation as easy as possible within different contexts. So you don't want to develop a specific type of model, for example, over and over again, just because you have a different simulation task you want to solve. So reusability is a really big motivation for in-depth spending attention on simulation architecture from the beginning. The optimization of tool setups is more easy looking at a good architectural design, especially when using different simulation tools from different vendors for different simulation setups. And even more, there are tier ones delivering hardware for the later vehicle, and so you need model to represent this hardware. And here again, you want to have a consistent representation of the models and an easy way to integrate these models into your simulation. So this will ease the OEM tier 1 or TN cooperation. If you have a really good system architecture design, it will ease process automation, which is, of course, a big factor in being faster in the development of your simulation and in the end development of a certain functionality and a certain aspect you want to develop and test. And finally, the architectural consistency. You want to keep along the whole process of the development, right from the beginning of the development, either of the whole simulation setup or a certain component of that. And by that, you will additionally gain process quality and traceability following that path. So you see there's a whole lot of motivation which justifies the time we spend within the project. And in the following, I will show you the results of those discussions we had throughout the course of our project. And we kind of summarized all this motivation and all these different aspects we had into 4 main project goals we wanted to achieve according to simulation architecture. And that is, we wanted to come up with a result where we have a consistency and a seamless chain between a high-level architecture description and concrete implementations. We wanted to apply simulation standards as a basis to make all these exchangeability more easily, and that's as well the third goal, to support the exchangeability of components as much as possible. And the last goal we pointed out here is that we wanted to come up with clear definition for interfaces and modules. And I will come back to that slide at the end of my presentation, and then you can see whether we succeeded in fulfilling these goals. You've seen this overview picture with the different levels of granularity of architecture design. And the idea is, as Stefan Rude explained, that we wanted to start with a generic description of the architecture and then adding more details to it bit by bit, and then coming to a concrete implementation, a concrete design of the architecture as basis for the implementation. And then do the loop back, learn from that, and feedback that into the higher levels of architecture design. So actually, throughout the course of the project, we did a few iterations through these different levels, and what I will present here is the result we came up with in the end. So, as a starting point, we had 2 very strong pillars. The one is the expert knowledge all the different partners within the project brought with them when we started the project. And you've seen in the introduction that there are really different partners from different areas, science, industry, which are part here of the project. So this was a great treasure to start with, going into that discussions. On the other hand, it brought some difficulties, of course, with it as well, because depending on what your background is, you might understand the same thing using different words, or the other way around. Same words were used for different things. So a lot of discussion in the beginning was about coming to a common understanding. And in order to ease that a little bit, we had the second pillar, the ASIM generic open testing architecture, which you find in the ASIM Sim guide. And if you look a little bit closer into that one and what we came up with, you will see that we use that as a basis, and you will see some similarities. But you will see differences as well, because throughout our discussions, we always had the focus on model and software in the loop simulation for highly automated driving. And of course, this is respected in the result of our generic open analysis and testing architecture, which is displayed here. I will now take you through this picture a little bit more in detail so that you have a little bit better understanding of our thoughts we had with that. And the main idea was to modularize here the different aspects of setting up a simulation, executing it, and then analyzing the results. So I will start with the simulation preparation, where you have a management interface which connects the simulation to surrounding processes like quality management, standard processes, or simulation-based engineering processes, which are established in the companies. You have the configuration management, where you take care about things like version control and traceability, and try to manage through all the process of the simulation development these aspects. Repositories are used for gaining from past setups, past experiences. So, and we try to add with our project as well to some scenario and traffic space databases. So this is respected here. And then we come to the more specific borderlines of the simulation tasks and the experiment setup, where you start to define what do you want to achieve, what is your task, your test or analysis task requiring, and go a little bit more then into simulation configuration to put the requirements, start to think about and put requirements on different aspects of the simulation. The lowest part is representing the generic bus, which interconnects all elements then later on in the simulation. For the execution of the simulation, we have the element of the scenario control as a top-level component, which controls the execution of the simulation and includes things like abortion criteria or setting time steps, which might be dynamically varied within different simulation runs. The simulation run itself is then controlled from a simulation platform control module, and then the execution itself, there we identified different areas where you can divide your simulation into, but we will see more of that in the more detailed levels. Then, of course, you have to store the data you produce as output of your simulation, and some logging, the processing of the logging of the data you produce is coupled to that. So that's the execution part of the simulation and of that architecture picture. And then we have the post-processing, where you run evaluation algorithms and some analysis, do some reporting tasks, which can be manually or automated. And you might retrieve some logged data for that and then store again the evaluation data. So, and maybe at the end you can add to the storage, to the repositories with some results. So you have seen that picture, and I will do a short excursion to the standards because they will be very relevant for the next level of detail of the architecture. And here I will shortly introduce FMI, OC, and SSP as quite tightly connected to the architectural design. And you will hear those abbreviations quite more often or see them on the posters. So I want to give you an impression what are these about a little bit more in detail. And the functional mock-up interface definition is saying that it is a tool-independent standard to support both model exchange and co-simulation of dynamic models using a combination of XML files and code. So we have two aspects here, model exchange and co-simulation. And in the respect to FMI, this means is a solver which might be needed in connection to a model. Is it included in the functional mockup unit, or is it excluded? And I will not go into details about the differences between those two ways of compiling an FMU, but when we talk about FMUs in the context of set level, we always used co-simulation FMUs. So if you see in the architecture views those blue boxes, it's that. Here you have some key facts, which I not will go into detail, but FMI is a quite mature standard already, which has some good tool support. And the main advantage I would like to point out is the co-simulation API, which allows for parameterization and synchronous simulation stepping. But it has other features which you can see here and look through in more detail afterwards. OC is the Open Simulation Interface, and it defines a generic interface between three main elements which it defines, and then that is the environment simulation, sensor models, and HUD functions. So only the communication between those three elements is standardized by OSI, and we used those standards, and furthermore, we defined some additional signals because the HUD function itself can be defined in various ways, how you define the subsystems within the HUD function. So here we had to define own signals, which we did according to the OSI message layout, but they are not standardized. So here again, key facts, and here I have to say that on the data layer level, a lot of the discussions we did and based on our tests, we could contribute to this standard throughout the project. So the version of OSI we used at the end of the project was already influenced by some results we obtained in the first half of the project. So there was a really active exchange with that group defining the standard. The last one is SSP, and that's a standard for configuration of FMUs. And here we looked into both how to generate files, SSP files, from an UML definition of an architecture, and here we used enterprise architect models for that, and we tested the usage of SSP in a couple of simulation tools. So you will get more information at the booth I point out here. So again, some key facts, but yeah, you have to look at them later on, because I'm a little bit running out of time. So the second level really should explain the usage of these standards. And how the different modules within the architecture are interfaced. So you see SSP, FMI, and OSI as very prominent connectors for the different areas. And these areas are filled with more details according to the simulation use cases, which have been explained before by Aaron Das. So that was our guideline for these simulation tasks. We wanted to implement these architecture or design the architectures and then implement it into different tools. And here again, I will not go into detail, but I wanted to show and point out that here already the strengths of this modular and flexible approach showed up, that we could use the same models in different contexts, the same simulation setups in different vendor tools or research tools or open source tools. So a lot of the things which we were talking about already, we could demonstrate them using these simulation architectures. One specific remark about one architecture and one tool, and that's the research implementation as an open source tool, which was developed mainly throughout the course of the project. And the special relation to the architecture is that right from the beginning, we tried to follow the architectural thoughts we had within the implementation of that open source tool. So especially here, you will find a quite close relation between the generic architecture and the design of that framework. So ending with one tiny specific example of a camera sensor according to the different levels. So on a generic level, you would define for a certain simulation task the need for a camera sensor. Then on the platform architecture level, where you think about the interfaces you want to use and the standards, you apply that. And then on the concrete level, you would define the exact in and outputs and pick a specific model and define all the details you need. So by that, you can have a stepwise configuration, and the other way around, a very good traceability between what you implement in the end and what you specified at the beginning. So coming to the project goals, I mentioned I will come back to that slide. We showed this seamless connection between high-level architectures and concrete implementations using Enterprise Architect and UML models. We used the standards within all the simulations. You've heard about that a lot by now. The support of exchangeability, I pointed out how we chose that based on our demonstration use cases, and the clear definition. They're quite a prominent example you can find in the research implementation. So the takeaways are that we derived a domain-specific architecture. We applied this idea and the concepts and showed the easy exchange of simulation model that is valid for that. I hopefully could show the advantages of using these standards and what it means for reusability of different elements. And we did a concept evaluation using the specific simulation use cases. So on this last slide, I just pointed out again which exhibition booths have a quite strong link to this presentation. So look at it, and you might want to go into more details looking at these exhibitions. Thank you.
Thank you very much, Dr. Fischer.